Let's get started. Enhanced Interior Gateway Routing Protocol is a Cisco proprietary protocol. Effectively, it's their second take on this protocol. It used to be called Interior Gateway Routing Protocol, which is now retired. Interior Gateway Routing Protocol was a competitor to Routing Information Protocol, and IGRP and EIGRP are Cisco proprietary, meaning that Cisco wrote and maintained the specification for it. Right now, EIGRP is listed in an RFC, so any vendor can read the RFC and implement EIGRP on their devices. However, for the most part, we do not see EIGRP being used on other gear besides Cisco gear. Additionally, we see EIGRP slowly dying as time passes. It does not mean that it's not used anywhere. It's just becoming a bit of an antiquated protocol, and other protocols that we have, like OSPF and ISIS, are more effective for modern networks typically. Let's take a look at how EIGRP operates and what its main features are here. EIGRP is a distance vector protocol. It has fast convergence like OSPF, and it uses a composite metric, which can give the administrator lots of options for building and maintaining their data network. First off, it's a distance vector routing protocol. What that means in this case is that EIGRP is going to exchange routing table information in order to populate a topology table. So we're going to synchronize these topology tables across all the routers in our EIGRP autonomous system, and the topology table is populated with the routing table information from its neighboring routers. This is unlike OSPF, where OSPF uses the link state database and link states to tell its neighbors what the state of each link is. So we're exchanging those link state information in OSPF. Here we're exchanging routing table information, which is effectively why we're calling this a distance vector protocol. Second, EIGRP has fast convergence. This is very similar functionally to OSPF. In order to get that fast convergence, we're going to keep three tables. One of the tables is the neighbor table, much like OSPF. We're also going to keep a topology table, which is just like OSPF's link state database. And then we're going to run an algorithm against the topology table to calculate the routing table, which is just like OSPF. The algorithm we use here for calculating the best path to the destination network is called dual, or diffusion update algorithm. What dual does is it calculates something called a successor route. Now, that successor route is the route with the best cost to the destination network. The route with the best cost to the destination network gets added to the routing table. In addition to calculating the successor route, which gets added to the routing table, OSPF also calculates something called a feasible successor. The feasible successor is the route to the same destination network as the successor route, but it has the second best cost to that destination network. What will happen is the dual algorithm will label that route in the topology table. And should we lose the path to the successor route, right, some network in the path that is the best cost path to that successor route, should that path become disrupted, what will happen now is the feasible successor route will be immediately added to the routing table when we lose that successor route. The diffusion update algorithm does not need to do any calculation for this to happen. So should there be two routes in our topology table that are destined for the same network, the dual algorithm will add the successor route to the routing table. Should we lose the successor route, the feasible successor gets added then to the table immediately. In my opinion, successor usually means it's the next thing to come, right? So if we have a president, the successor president is the one that comes next. Here, we're talking about a successor route, and an EIGRP that means the best route. The feasible successor here is the second best route. Last, EIGRP is going to use a composite metric. This is both a benefit and a bit of a pain here, because it leads us to believe that EIGRP can do things well that it probably can't. At any rate, this composite metric means that we're going to take 4 values here, or potentially take 4 values, and combine them together to determine the cost to the destination network. By default, we're going to use bandwidth and delay of line to calculate that. The bandwidth is a configured value. By default, the router will set the bandwidth of the interface typically based on the actual bandwidth of the interface. However, the administrator can configure that bandwidth to be whatever we need it to be so that we can control the path to our destination network very easily. We can do the same thing with the delay of line calculation as well. So EIGRP gives us 2 values that we can use that are configured on our interfaces to calculate the cost to the destination network. Additionally, EIGRP can use calculated values. So our interfaces will also pay attention to the load that is passed across the links that we're using here in EIGRP. The interfaces will also pay attention to something called reliability, which is how often the link is in the up state and passing traffic. These calculated values sound like they could make EIGRP a pretty nifty protocol. However, we very rarely use these calculated values. And the reason is that since those values are dynamic and they change, we have no idea when EIGRP is going to have a topology change and recalculate the routing table. By using these calculated values, we run the risk of having EIGRP constantly updating the topology table and rerunning the dual algorithm. And as a network engineer, typically what I want is a very predictable network, because a predictable network means that should there be an event that causes a network outage, if I can predict the way the network is supposed to behave, I can then use that information to help me troubleshoot what's wrong when the network is broken. If I'm using these calculated values, I really have no idea what EIGRP is doing. It kind of becomes a thing on its own, and that may not necessarily be the best way to administer a network. So my personal opinion is that we do not use these calculated values in EIGRP, and I suspect in the real world, you will almost never find a network using those calculated values. In fact, as a network engineer, I would never, ever use calculated values in my network. I always want to use those configured values. Now, that could change over time, but for the time being, to make a predictable network, we're going to stick with those default configured values for our metric.